This presentation is on soil conditions and soil testing. So prior to developing a property for commercial endeavor, a designer needs to investigate the soil conditions at the site. There is no construction material that has both the physical engineering properties that are more variable than soil. Therefore, it is highly desirable to have some information regarding both the surface and subsurface soil conditions. Soils, so what is it? Well, soils rarely exist as separate components such as sand or gravel. Soils contain various particle sizes of gravel, sand, silt, and clay, and for each contributes to the characteristics of the soil. So why test the soil? The knowledge gained from soil testing allows the engineer to make estimates for bearing capacity of the soil, the settlements of the foundation, both the amount and rate, the earth pressure, both lateral and vertical, and drainage. And these characteristics determine how certain soils will behave as a construction material. What is needed to determine soil properties? Well, in order for the engineer to determine the soil type of soils and for the building and characteristics of that soil, a site plan, a contour map, or site profile, and a geological survey map for the area are needed, in addition to the soil's property information that will be obtained during testing. There are several factors that need to be considered when determining the type of foundation you will need. The soil type and the soil condition is a major factor in the engineering decision. The function of the structure refers to the type of building, such as an educational, small commercial, or heavy industrial building. Each type of building will have vastly different building loads due to the building materials selected and the live loads imposed on the structure. The bearing capacity of the foundation material refers to the strength of the soil, which is determined by investigated soil techniques. The settlement of a structure can be a result of under-designed foundation system, poor soil conditions, or unknown or undetected soil conditions. And uplift forces refer to the imposed loads from the soil and groundwater acting on the foundation and can cause the foundation to be pushed up, yielding unwanted cracks in the foundation or failure. The soil bearing capacity is determined by the geotechnical engineer. It can be based on governing building codes, on soil analysis and testing, or by past experience with similar tools in the regional area. Geotechnical engineers accumulate information on the successes of their designs in the area and use these as a basis for future designs. It is easy to see that engineering judgment can play a role in the analysis of the soil. Engineering judgment should not be confused with the best guess. When engineering judgment is used, the soil bearing capacity can be assumed based on some of this information. This is known as the presumptive bearing capacity of the soil. The presumptive soil bearing capacity is typically a lower bearing capacity value that could be determined through soil testing. When taking soil samples, the location and the depth of the soil samples should be representative of the soil at the site. Soil samples are typically taken where the building foundation will be located and where the septic system will be located. Other locations can be selected to confirm the soil results. Keep in mind that the soils throughout the site may or may not be uniform. There could be outcroppings of rock or other soil types that you do not locate within the site. When this happens, the engineer must be able to determine if these samples are representative of the site or should additional soil testing be required. The Unified Classification System is a rapid method for identifying and grouping soils. It was first developed for military construction of airfields. Many soils can be grouped visually within the USGS with additional tests for grain and size and plasticity required to accurately classify the soil. Just to show here that the Unified Soils Classification System is quite often called the USGS for short. So a little bit more on this Unified Soil Classification System. We are going to look at soil testing methods that provide information about the size of the soil particles, the percentage of various sizes of soil particles, and the characteristics of the very fine grains within the soil sample. The Unified Soil Classification System is based on the results of a test that determines grain size and distribution of the soil samples. Only particles smaller than 3 inches are considered in this USCS system. So let's take a look at coarse versus fine-grained soils to get an idea. While many soils can be visually or grouped visually with the USGS, and additional tests for grain size and plasticity are required to accurately classify the soil. The coarse grained soils are described by the grain size. The fine grained soils are described on the basis of their plasticity. Soils are a mixture of gravel, sand, silt, and clay. Gravels range from about 3 inches down to the size of peas. Sands start just below this size and decrease until the individual grains are just distinguishable by the naked eye. The eye can normally see individual grains about 0.07 millimeter in size, or about the size of a number 200 sieve. Silt and clay particles, which are smaller than sands, are not distinguishable as individual particles. So here's a look at some of the sieves with a number 40 sieve which has a similar window screen, but the size of the mesh is a lot different compared to the number 4 sieve, which has 1/4 inch squares, pretty much similar to hardware cloth. Okay, there are many different types of soils, such as rock, gravel, sand, and clay, and silt. The soils that we encounter are a heterogeneous mixture of 3 basic types. The gradation of the soil particles range from boulders, which are over 12 inches in diameter, to silt and clay particles that are so small that they cannot be individually distinguished by the naked eye. Coarse gravel from 3 inches to 3/4 inches, samples that were retained using the number 4 fine gravel from number 4 to 10, samples that were retained on both, and the number 4 and 10 sieves. And you can see in these jars the size of these gravels, and they actually come up with different names like plum or lemon, or grape or pea. So coarse gravel from 3 inches to 3/4 inches, these samples were retained for the number 4 fine gravel from number 4 to 10, samples that were retained on both the number 4 and number 10 sieves. And here again we have the coarse sand obtained from the number 4 to number 10, which is comparable in size to about rock salt. And then the medium sand, which is sometimes it's even called sugar sand, is comparable in size to sugar. And coarse sand, like we say, is pretty much equivalent to rock salt, medium sand equivalent to sugar, just to reiterate that. Soils are described by their gradation characteristics. A well-graded soil is defined as having a good representation of all particle sizes from the largest to the smallest. Poorly graded soils are divided into 2 types. A uniformly graded soil consists primarily of particles of nearly the same size. A gap-graded soil contains both large and small particles, but the gradation continuity is broken by the absence of some particle sizes. A gravel or sand soil type can be classified as clean or dirty, depending on the percentage of fines within the soil sample. If a soil identified as being clean, it contains little or no fines, less than 5%. If a soil is identified as being dirty, it contains an appreciable amount of fines, silty fines or clayey. And again, the fines are just another industry term for the very fine particle type, and that's where clays, you can never really see those individual particles as it is, if you were to look at it with the naked eyes. So soil designations. So the USCS divides soils that have not been classified into the major soil categories by the letter symbols, such as S for sand, G for gravel, M for silt, C for clay, O for organic, and PT for peat. Just to say, peat should never be built on. It's just not stable, not a stable soil. It should almost not be considered a soil, in my opinion. So when examining the samples for grain sizes, the shape of the visible particles can be determined. Now, here we have shape making a difference too. Sharp edges and flat surfaces indicate an angular shape. Smooth curved surfaces indicate a rounded shape. Particles may not be completely angular or completely rounded. These particles are called subangular or subrounded, depending on which shape predominates. Platy is a name given for those particles which have one dimension. Color helps in distinguishing between soil types, and with experience, aids in identifying the particular soil type. Color may also indicate the presence of certain chemicals or impurities. Color often varies within the soil's moisture content. Colors in general become darker as the moisture content increases and lighter as the soil dries. Some fine-grained soil with dark drab shades of brown or gray, including almost black, contain organic colloidal matter. In contrast, clean bright shades of gray, olive green, brown, red, and yellow, and white are associated with inorganic soils. Gray, blue, or gray and yellow mottled colors frequently result from poor drainage. Red, yellow, and yellowish brown colors result from the presence of iron oxides. White to pink may indicate considerable silica, calcium carbonate, or aluminum compounds. Plasticity of the soils refers to the varying water content on the consistency of the soil in fine-grained soils. The system is referred to as the Atterberg limits, named after the Swedish scientists who developed this test. And to say the plastic limit is the lowest moisture content at which soils can be rolled into the 1/8 inch diameter thread without breaking. And the liquid limit is the minimum moisture content at which soil will flow when a small shear or cutting force is applied. The letter symbols are derived from the soil fractions of gravel, silt, clay, organic, or peat, the relative gradation of the soil's particles, and the value of the liquid limit. These letters are then used in combination to form the soil's groups. Okay, determining the silt or clay characteristics of fine-grained soil. In addition to the sieve analysis, the following tests will be done to make a determination of the fine-grained soils. And dry strength, well, that will show crushing characteristics. Dilatancy is a reaction to shaking, and toughness is consistency near plastic limit. Here again, we'll take a look at an output from the Unified Soil Classification System, just to see how this looks all together in a page form. And the major divisions, again, are coarse-grained soils, fine-grained soils, and highly organic silt. Starting with how much of the soil sample by weight is retained on the number 200 sieve. One can determine if it is a coarse-grained soil, a gravel, or a sand. If more than 50% of the soil particles pass through the number 200 sieve, then the sample is a fine-grained sand. Coarse-grained soils are defined as those in which at least half the material is retained on a number 200 sieve. So here's some of the equipment that you can use for testing, or you will need for testing, and you can see there's nothing really, it's not as complicated as one might think, especially where you see that you're going to need to take a couple of samples of soil about the size of a coffee can, so you can actually use a coffee can to get an idea of that. And a couple of samples, just to know, have to be collected below the top soil horizon, which is about 1 to 2 feet below the top ground level, is what they mean by the called soil horizon. A couple of mason jars with tops, a 5-gallon pail, water, mixing bowl, a 2-inch by 2-inch metal pan, and rubber mallet. And then the sieve collection. Maybe that's the most complicated thing here, basically, because you have to find sieves that are what they are is by ASTM approved, that they're a referenced standard. That's all. They're just a body like UL or United Laboratories that decides and governs the engineering of a certain thing. So basically, you need sieves that are number 4 and number 40 in the bottom, and the bottom sieve pan and cover. And again, they just have to be approved by ASTM, and a triple beam balance or digital scale. Next, we're going to look at testing and actually how this looks in the field. This section is a lot more graphic and has a lot more visual references. So this is how you would weigh each of the sieves. Now, weighing each sieve individually, the pan and mason jar without the lid for later, keeping that aside for later use, the lid. And remember, we are using number 40 and a number 40 and a number 4 sieves. That's how we'd start off with this. And then, in taking a representative soil sample, we presume that it is representative of the soil and other locations of the property. Soil is not a composition of sand, gravel, silt, and clay, and is not homogeneous material. Therefore, the soil in which the soil is taken from should be in areas which the building foundation will be located. A shovelful or coffee can full of soil should be enough to complete the soil analysis. So the soil sample should be dry, preferably dried under low heat, less than 200 degrees Fahrenheit, for a few hours. And if that's not possible, let the soil dry inside for several days. Pulverize the soil either with your fingers or a rubber mallet. Be sure that all small and large clumps are completely broken apart. Remember that the sample should not contain rocks greater than 3 inches in diameter. So continue to pulverize the soil with your hands. Be sure that all the small and large clumps are completely broken apart. Stack the sieves with the number 4 on top, then the number 40 sieve below that, and then finally the bottom pan. And note the amount of soil put into the sieve. Again, a shovelful of soil is enough. So place the soil in the number 4 sieve, place cover on top, and shake vigorously. Remember that was that first test, the shaking test? Dilettancy. Shaking the soil sieves, you can shake the sieves with an up and downward motion and also use a side-to-side shaking motion. The goal is to separate the soils into the 2 sieves and the pan for fines. Do not shake the sample so hard that the lid falls off or you drop the pans. Otherwise, you will have to start over. Put the cover off of the number 4 sieve and inspect its contents to be sure that small dirt clumps do not exist in the number 4 sieve. Then manually break up small dirt clumps and shake again. Now let's take a look at another process, weighing the weighing of each sieve with the sample particles. So record and subtract the weight of the number 4 sieve only, without the soil sample. The difference is the gravel fraction in the soil sample. Then record and subtract the weight of the number 40 sieve only, without the soil sample. The difference is the coarse and medium grain sand fraction of the soil sample. Then weigh the bottom pan and its contents. Record and subtract the weight of the empty pan. The difference is the fine sand, silt, and clay fraction of the sample. So in each case, what you're doing is you're weighing the two together, the pan and the material inside, and then simply emptying it out and then moving the pan to the side and weighing the pan separately so that you can minus it from the total and get that final amount. That way you know exactly what the material that was in the pan weighed. It's just the process that's followed. There are obviously other ways to do it. So by weighing the sample retained in the sieve, we could see how much the sample by weight was retained. Then we could compare it to the USCS chart and determine whether it is coarse or fine-grained soil. That's how it goes. So record and subtract the weight of the number 40 sieve only, without the soil sample. The difference is the coarse and medium grained sand fraction in the soil sample. Weigh the bottom pan and its contents. Record and subtract the weight of the bottom pan. The difference is the fine silt and clay fraction of the soil sample. And shown here is the relative difference in particle size in this particular soil sample. This would be considered a coarse sand because more than 50% by weight of the soils is retained on the number 4 sieve. And here's a comparison of coarse gravel, fine gravel, and coarse sand next to the number 40 sieve. Again, that's a 1/4 inch square mesh. So the USCS classification for grain soils. After you have sieved the soil, you need to determine whether the soil is coarse or fine-grained soils. A coarse-grained soil, also called a granular soil, has more than half of the soil grains visible to the naked eye. If the percentage of gravel and sand is greater than 50%, then the soil is granular soil. If the soil is predominantly coarse-grained, identify the soil sample as being gravel or sand by estimating whether 50% or more by weight of the coarse grains, gravel and sand, and larger or smaller than the number 4 sieve size. So fine-grained soils are also called cohesive soils, and they contain greater than 50% of silt and clay particles. The fine-grained soils are classified further into either silt or clay, and then determine if it is have a high or low plasticity by estimating the dry strength, which is crushing characteristics, the dilatancy, which is the reaction to shaking, and the toughness, consistency near the plastic limit. The individual fine grains are not visible to the naked eye. Just keep that in mind. So pour the contents of the bottom pan into the mason jar, weigh and record the weight, and the water to the jar. Add water to the jar so that 3/4 of the jar is filled. Place the top on the mason jar and shake the jar. Allow the fine sand to settle for 5 or 10 seconds. Remove the top and pour off the dirty water into a 5-gallon pail. Be careful not to spill any of the soil that is settled to the bottom of the jar into the 5-gallon pail. Repeat until the water is clear. The material remaining in the mason jar is the fine-grained sand, silt, and clay that has been removed from the soil sample. So next, remove the top of the mason jar and pour off the dirty water into a 5-gallon pail. And be careful not to spill any of the soil that is settled at the bottom. Again, repeat until the water is clear. You may have to do this several times. The material remaining in the mason jar is the fine-grained sand. The silt and clay has been removed from the soil sample. So determining the weight of silt and clay in the soil sample, and to determine the weight, place the mason jar without the top and the contents into the oven and let the sample dry. Then remove the jar, being careful since the glass will be hot. Weigh the jar and contents, record the weight, and subtract the weight of the empty jar. The difference is the fine-grained sand fraction in the soil sample, and determine the weight of silt and clay in the soil sample. So the dilatancy test, remember that's the reaction with wet shaking. Prepare a pad of moist soil with a volume of about 3 inches. Add enough water if necessary to make the soil soft but not sticky, like soft putty. Place the pat in the open palm of one hand and shake horizontally, striking it vigorously against the other hand several times. Observe the rapidity of water rising to the surface when the sample is shaken and when the sample is squeezed between your fingers. The speed of appearance during shaking and disappearance when squeezed assists in identifying the fines in the sample. If the sample becomes soft and glossy when shaking, and then becomes hard or dull and forms cracks while squeezed with the fingers, it has a reaction to shaking or dilatancy. So based on the reaction when you shake and squeeze the sample, very clean sands give the quickest and most distinct reaction. A rapid reaction sample is silt, M, an M class. No reaction indicates clay, the C or C class. So the toughness test is a method of testing the plasticity of the soil, and that is why it's called the toughness test. Water is added to the fines portion of the soil sample, those particles that pass through the number 40 sieve, and the sample is then rolled into a 3 millimeter or about a 1/8 inch diameter thread. So mix about 100 centimeters, about a third of a cup, with water and mold it to the consistency of putty. If it's too dry, water must be added, and if it's too sticky, the specimen should be spread out on a thin layer, and allowed to lose some of its moisture by evaporation, or you can add a little bit more soil. The specimen is then rolled out by hand on a smooth surface between the palms into a thread about 3 millimeters, so that's approximately an eighth of an inch in diameter. The thread is then folded and re-rolled repeatedly, and as you do this, the moisture content is gradually reduced and the soil specimen stiffens and finally loses its plasticity and crumbles when the plastic limit is reached. After the thread crumbles, the pieces should be lumped together and a slight kneading action continued until the loop crumbles. The tougher the thread near the plastic limit of the stiffer lump when it finally crumbles, the more potent the colloidal clay fraction in the soil. So here is the thread test, just to take a look at it, how you roll it out. Pretty much looks a lot more like a bakery type thing than a soil test if you hadn't seen this before. So here's the toughness test results. The toughness of the thread that forms when the soil is rolled will identify the fines as either silt or clay. So an inability to form thread or very weak thread indicates a plastic silt, Ml, and weak spongy thread indicates silt, either organic or inorganic, and a high liquid limit with a low plasticity pretty much shows that it's an MH type classification. And firm thread indicates low plasticity clay, Cl, and tough thread indicates the high plastic clay, CH. So here's another test. It's called from the dry strength. You form a moist pat of approximately 2 to 3 inches of diameter and a ½ inch and allow it to dry with low heat. The crushing characteristic of the soil sample will be evaluated after the sample is completely dry. And here is some of the results for the dry test. If you can break the dry pat of sample between the thumb and finger, well, if breakage is easy, it's silt. If breakage is difficult, it's inorganic clays of low to medium plasticity. If breakage is impossible, that means it's inorganic clays of high plasticity. So here are some of the summary of tests that are performed on the fine-grained portion of the soil sample. This is how it would look like. You've done your dry crush test, you've done a dilatancy test, and a toughness test. They're all shown there on the very top of the table. And from that point, you fill in the categories as to how you feel, how each of these tests ended up turning out for you. But let's translate that now into what happens for foundations. Well, sand and gravel are the best soil types for foundations. and medium to hard clays are good. Soft clays and silt, well, they're poor. And organic silts and clays are totally undesirable, and peat is no good and should be avoided. So let's take a look at some of the soil bearing capacities. And we get these tables are pretty much made from the historic type information, past engineering information. But you see the bedrock, of course, is probably can take the most amount of bearing. Of course, nothing like building with solid rock. Gravels, well, they're pretty high up there, but they're in the 3,000 pound per square foot range. And the gravel with fines, pretty much about the same as gravels altogether. Then it drops a bit with sand, and drops even further with silt and clays. And organics, anything organic, trying to build on that is just, well, it's going to have poor drainage. You can see the whole drainage item is given to the right. Of course, that gains the same amount with the organics as poor drainage, as so does bedrock. So you got both ends of the spectrum getting the same rating as far as drainage is concerned. So what about soil preparation? What if the site has poor soils? Is there anything that can be done? That's the question. And if the soils of the site are not suitable to carry the foundation loads, the site might have to be prepared using some of these following methods. Well, compaction of the soil. You can increase the density of the soils, and that therefore increases the bearing capacity of the soil. Compaction of the soils is done by rolling with soils. Or you could bring in engineered fill, but most remove old soils first. Or you could do blasting to remove rock or soil. So here's another chart of some of the soil types and properties. And soil types and their value as a foundation material is very important. From the chart you can see the gravel and gravelly soils are the best for a foundation material, followed by the well-graded sands or gravelly sands. Again, taking a look at the charts here as we move down, silts and clays, and right there on the bottom is the highly organic soils, and they're not really suitable as a foundation material altogether. As low as silts and clays altogether are pretty poor in the same idea. So let's again, soil description. Look at the color, is usually dark brown or white. We look at the grain size, including maximum grain size. Remember that number 200 sieve. The main thing, the soil description should describe the significant properties of the soil. And many soil properties that are of interest should be provided. And if you are unable to obtain the soil property, you will have that list. You must have that listed in your description. So this is an example here of a soil sample. The soil description is noted in red. The soil's description can be written in paragraph form or just listed as shown above. The description should be noted on the drawings for a given project. So this is exactly what you want to see on, or should see on projects, and might have even seen in the past, right there on the blueprints, right on the plans. So a little bit more about soil description. You should have this in there too, the plasticity type. Maybe it's non-plastic. Predominant type, what is predominantly in the soil. Here it is, gravel. Your secondary components, considerable sand and trace amounts, and then finally give it a classification symbol. Here GP would be poorly graded gravel, for example. Then make other remarks such as the organic, chemical, and metallic content, compactness, consistency, cohesiveness, near plasticity, and dry strength and source. So thank you for looking at this presentation. You've got an idea of how the soil testing is done. They're not complicated. They're pretty much they're pretty easy to do. And once again, thank you for looking at this, and just remember those outputs about the how that final soil conditions test is put into a paragraph form and then placed on the blueprints.